Well, hello there. Tonight we're going to talk about conditional probability. And I'm going to extend our previous example into kind of a next level conditional probability. But before I get into it, let's review kind of where we are. And I want to show you this with a tree diagram and show you how we multiply probabilities down the branch. Students often get confused with probability because they think, well, does that mean you had to get, how do you know you got two heads? For example, if we flip a coin. And my response is we don't. We're just trying to list the possibilities and then the percentage chance of those outcomes. Let's take a look. So let's say we flip a coin. We have two outcomes, heads or tails. If we then flip that coin again, we could go heads or tails. And from here, heads or tails. And then if I flipped it again, I would have two more outcomes for each of those. 2 times 2 times 2, right? The 8 outcomes. But let's just look at two coin flips. So we know that this probability is 0.5, and this probability is 0.5. From here, I know that this probability is 0.5, and that probability is 0.5. Same here. So the final outcome down here is a head-head. Well, what's the probability of getting a head-head? 0.5 times 0.5, right? So we multiply those two probabilities. How about a head-tail? Same thing, 0.5, 0.5. Do you see how I'm multiplying down the branch here? Tail-head. Same thing. And then tail-tail. And look at the end. All of those add up to 1. These are our probabilities. So now we can answer the question, what's the probability of getting two heads? Well, that's 1 out of 4. The probability of getting a head and a tail. Well, if the order doesn't matter, then that's 1 out of 2. And then the probability of two tails has to be 1 out of 4. But the reason I show you this example is because I want you to understand how we multiply down the branch of the tree. So let's take a look at that for a second. Press pause, take a deep breath, because we're going to extend this simple coin flipping problem into something a little more complicated, but something we kind of deal with every day. Let's talk about the enzyme immunoassay test for HIV. Okay, so again, as with a lot of drug and disease testing problems, here's the situation. We know a certain percentage of people have this disease. We just don't know who they are. And so what we're going to do is we're going to test them. We test for antibodies, right? Because we assume if your body's produced the antibodies, you have the disease. But the problem is the tests are not 100% accurate. So that's why, as we said in the last video, the prevalence is really, really important. Okay? We're going to take this prevalence to be 1%. 99.85 sensitivity. That means if you have the antibodies, if you're HIV positive, this test is 99.85% accurate that it's going to find them. We're 99.4% specific. That means if you don't have the antibodies, the test will not find those antibodies 99.4% of the time. Now, those percentages sound pretty good, but as we're going to find out, they're not perfect. So the question number 1 is, let's find the probability you're HIV positive given a positive test. So you go in for your AIDS test, it comes back positive. Then we're going to take those samples and run them a second time. And then let's find the probability that you're HIV positive after a second test with the same sensitivity and specificity. What do you think the answers would be to those questions? Do you think you can figure it out? I'm going to show you a method tonight using natural frequencies, thank you, Gerd Gergerenzer, that might help. Let's take a look. Let's start with 1 million people. Now I'm choosing 1 million because I think I am going to end up dealing with a fractional person, but not until the very end. So you want to choose a big enough number so you don't have to deal with fractional people. Well, what do we know? We know that 10,000 people are HIV positive. We know that 990,000 are not. And the question is, how do we figure out which ones are positive? Because the disease is not 100% accurate. So let's run the test. So the first round of testing. So here we go. Of the 10,000 that have the disease, the test is 99.85% accurate. That's what sensitivity is. So we know 9,985 will test positive, okay? This is what we're going to call a true positive. Now, unfortunately, 15 will test negative. This is the false negative. Now think about the implications there for a minute. These are people who go in for the test, have it, but the test comes back negative. Now it's very few people, but still it's 15 out of 10,000. Now, let's go here. Of this 990,000 people that don't have the disease, 99.4% will test negative, as they should. And these are our true negatives. So this number here is 984,060. And all I did was just multiply 990,000 by 0.994. These are what we call the true negatives. Now, but 0.0 or 0.6% or 0.006 are going to test positive. Okay, this number here is 5,940. These are what are called your false positives. You often hear about false positives in the news, don't you? Every time an athlete gets a positive steroids test, they say, oh, it's a false positive. I didn't do anything, or it was just lotion, or I was getting a massage. I can't even think of all the excuses they've used now. False positive. Okay, so let's answer the first question. Find the probability that you're HIV positive given the positive tests. Oh, I think we can do that, don't you? Because we know how many positive tests we have. What's our denominator? It's the positive tests. 9985 plus 5940. Now of those, how many are actually positive? 9985. That comes out to be about 0.6270, or about 62.7%. Does that make intuitive sense to you? So you're saying if the test comes back positive, there's a 62.7% chance I'm HIV positive. That means there's a 37.3% chance that I'm not. So don't play a role in that Matthew McConaughey movie yet, right? Don't sell everything and move to Florida or Mexico. There's a 37.3% chance you don't have it. Well, doctors know that. So what they do is they say, okay, for all of those samples, we're going to test them again. We're going to take the positive results, and we're not going to tell the person they're positive. We're going to test them again. Okay, so remember that number, 0.6270. We'll get back to that. And let's just slide back over here now. Of these true positives, when we test them, right? So again, this 9985, this is just like the 10,000. These people actually have the disease. So again, I'm 99.85% sensitive. So 99.85% of 9985 is 99.7. That still leaves 15 here I mean, it's the same number because it's just a small percentage. About 15 here that are false negatives. But again, these are your true positives. And these would be another round of false negatives. How about these over here? Well, these people don't have it, right? And so when we test them, 99.4% should come back negative. And sure enough, they do. Okay, this becomes 5904.36, and this is 35.64. So these would be your true negatives and your false positives. So even after a second round of testing, out of that million people, there are 35 who still test positive even though they don't have it. Scary, isn't it? So just remember, 99.85% sounds really good, and 99.4% sounds really good, but when you're dealing with millions and tens of millions and hundreds of millions of people, man, it starts to add up. Okay, let's recalculate that. Let's see if we can answer that second question. What's your new percentage positive? Well, so let's take a look at those numbers for a minute. Let's just make sure we understand what's happened here, just like flipping the coin, right? We start with 1 million people. 10,000 of them, we just don't know which, are HIV positive. We do the first round of the immunoassay test, and we get, now that 10,000, 9,985 come up positive. We're going to run that test again, and 9,970 come up positive. On the other side of this group, 5,940 come up positive. When we run the test again of that group, 5,904 will go away, but 35 will still come up positive. So we're still not 100% accurate, but let's see if we can answer this question with the second probability. So here we go. So we've got the second positive test. So what's my denominator? 9970 plus 35.64. What's my numerator? The actual positive number that came up, 9970. And so what happens is this comes out to be 0.9964. And that's a number that, believe it or not, most people are going to live with. They'd love for that to be 100%, but they're going to live with 99.64. So this is what happens here with these problems. We've got a conditional probability, and the basic condition is we have a prevalence of 1%. We then have a sensitivity and a specificity, or a false positive, false negative. And I really believe that when you look at this with natural frequencies, the numbers really help you understand what's happening. Now, you're going to find formulas in your textbooks, Bayes' theorem, and other ways to calculate this. More power to you. Go right ahead. I believe that once you understand what's happening here and what's happening here, the formulas will help you make sense. But don't get bogged down with the formulas. At our level, right, advanced high school, introductory level undergraduate, what we really do want you to understand this stuff. So have a little fun thinking about this. And the next time someone talks about false positives and false negatives, you tell them, hey, I know what you're talking about. Have a great day. See you next time.